Welcome back everyone to the final video here in 1.7. In this video, right, our goal is to actually demonstrate how can we use this precise definition of the limit that we developed this last time. So, our first example, we would like to prove that as x goes to 1, our function 3x minus 1 goes to 2, right? And that kind of makes sense if we were to use our intuition and the direct substitution property. If I just plug in 1 everywhere I see an x, I would get 3 minus 1 equals 2. But I'd like to actually prove this using the formal definition of a limit, or the precise definition of the limit, if you'd like. All right, so remember, the precise definition of the limit says that we can make this f of x and this 2 as close as we would like to each other. So I'm going to go ahead and write down this f of x, 3x minus 1, and 2 as close as we would like. So whatever distance away that we'd like, we use the value epsilon in this case. So our goal is to make this f of x and this L within distance epsilon of each other. In order to do that, we're going to restrict, right, how close does x need to be to this a value. So x minus our a value here is 1. And the question is, how close does x need to be to 1 in order to make f of x within distance epsilon away from 2. Okay, so first of all, we're going to have a bit of scratch work. This is going to be a formal proof, so there is going to be a proof component to this, but before we get to that part, there's going to be quite a bit of scratch work going on. So I'm just going to write scratch work, and I'm going to do this all in green. This is necessary in order for us to be able to do the proof. We wouldn't be able to guess kind of the outcome of this. But it does take a little bit, and it's not the formal proof part. Sometimes people confuse that the scratch work is the formal proof part. It's not. Okay, so again, we want to know how far can x move away from 1, right? Or how close really does x need to be to 1? Notice we're not using d anymore, we're using delta, the Greek d, essentially. So how close does x need to be to 1 so that our function is within distance epsilon from 2. All right, so staring at this, we probably can simplify it down a little bit. 3x minus 3 is less than epsilon. And sorry, there's going to be a lot of 3's and epsilons flying around here. You have to make sure that you write the correct one down. Okay, so staring at this, it may be difficult to get a distance statement from this. I'm going to go ahead and rip this apart using our nice theorem that we had from our first video. So that's going to say negative epsilon is less than 3x minus 3, which is smaller than positive epsilon. Now I'm going to add 3 to all sides. So I get 3 minus epsilon is less than 3x, which is less than 3 plus epsilon. And then I'm going to divide everywhere by 3. So let's see, if I divided the left-hand side, I would have 1 minus epsilon over 3 is less than x, is less than 1 plus epsilon over 3. So let's draw our second number line here. Here's 1. And it looks like, okay, this is kind of a strange value here, but I can go down epsilon over 3. So I go down, this length right here would be epsilon over 3. Oops, back. Epsilon over 3 to this value, which again would be 1 minus epsilon over 3. And I could go up epsilon over 3, right? 1 plus epsilon over 3. So epsilon over 3. And that's going to get us, again, to here, 1 plus epsilon over 3. And so long as I'm within this region, right, the claim is our function is within distance epsilon away from 2. So we can go down to 1 minus epsilon over 3, and we can go up to 1 plus epsilon over 3. So the question again is, how far can x be away from 1? Or really, how close does x need to be from 1 so that this is satisfied? Well, it looks like I can go down epsilon over 3, and I can go up epsilon over 3. So delta, our distance that x needs to be within from 1, right, should be epsilon over 3. So whatever value of epsilon you specify for me, whether it be 1/2 or 1/100th or 1/1,000,000th or whatever, I'm going to take that value, I'm going to divide it by 3, and that's kind of the region that I need to restrict x to be in so that my f of x is close enough to this limit 2. So again, this is the scratch work. This is finding the correct delta value. So now, for any epsilon, we were able to find a good delta value. And so I would like to prove that this is now true, right? So that if x and a are within distance delta from each other, then f of x and L are within distance epsilon from each other. So here comes the formal proof. So I'm going to take delta to be equal to epsilon over 3. And we're going to go ahead and suppose that x minus 1 inside of the absolute values is less than distance epsilon over 3. Right? So x and 1 are within distance epsilon over 3 from each other. And now I like to use a sequence of steps here, right, logical math steps, that let us prove then that f of x and 2 are within distance epsilon from each other. Okay, so more or less, this is going to be just working in reverse a little bit. So I'm going to multiply by 3 on both sides. So I'm going to get 3. Absolute value of x minus 1 is less than epsilon. Okay, now I'd like to use, let me interject a nice theorem here for absolute values. So you have the absolute value of quantity A times an absolute value of quantity B. This is the same thing as the absolute value of A times B. And I want to use this to push this 3 inside of the absolute value, right? Because of course 3 is the same thing as the absolute value of 3. So I'm going to write this as the absolute value of 3x minus 3. So I just push this inside using this nice theorem here, and I distributed. And so the last step, I'm going to go ahead and rewrite this, right? My goal is to make this look like this up here. So I'm going to write 3x minus 1 minus 2, so this is my f of x, minus my L, is less than epsilon. So if this was true, we were able to prove using some mathematical steps that are all correct and mathematically sound that f of x is within epsilon of 2. So this, again, is the formal proof part. Don't forget about this. All right, one example down, again, trying to use this precise definition. Let's try something a little bit more difficult now. So this was a nice linear function. Now let's use one where we have a quadratic function. So again, I would like at the end of the day that no matter what epsilon value you give me, I have f of x, and my limit, which is supposedly 16 in this case, should be within distance epsilon from each other. In order to do this, I'm going to restrict, right, where my x is. I want it to be close to my a value. In this case, my a value is 5. So I'm going to try to go out and find a good delta value so that the function and 16 are as close as you want, within distance epsilon from each other. Okay. So again, we're going to have some scratch work here. And I'm going to cut it out with all these number lines and stuff that I've been doing. I'm going to kind of just purely, algebraically solve this one. So okay, the scratch work here, I'm going to go ahead and write out my specific f of x. So x squared minus 10x plus 41 minus my 16 is less than epsilon. I can combine like terms. Let's do that. X squared minus 10x plus 25 is less than epsilon. And now staring at this for a little bit, I notice that actually this is a nice perfect square. That I can rewrite this as x minus 5 quantity squared. So double check. If you were to FOIL this all out, you would get back to this step right here. So if you FOIL this, you get here. But this is nice, because now I'm allowed to, well, I see the square, I'm going to go ahead and take the square root on both sides. So this is going to give me the absolute value of x minus 5 is less than the square root of epsilon. And so again, my goal is to try to make my function within distance epsilon away from 16. In order to do that, I was able to find, through a system of math steps here, that if x is within distance square root of epsilon of 5, we stand a pretty good chance of making that happen, right? To some extent, notice how close that these things are. I was able to make this look like, well, here's an x minus 5 part, and I'm trying to choose a delta value. So the claim is, if I choose the delta value root epsilon, then this will be a good distance right, that x can be away from 5 so that my function is within distance epsilon from 16. So, okay, again, that was the scratch work. Now let me show you the formal proof. So we're going to go ahead and let delta be equal to root epsilon. And we're going to suppose, right, if this is true, we're going to show that this is true. So let's see, x minus 5 is less than delta. And again, delta is root epsilon. That's my choice anyway. And now again, almost working in reverse. I'm going to square both sides. So I'm going to get x minus 5 quantity squared is less than epsilon. Let me go ahead and distribute. So I'm going to have x squared minus 10x plus 25 is less than epsilon. And now let me go ahead and rewrite this, right? I'm going to break up this 25 in this very silly way for plus 41 and minus 16. And of course I do this because this is my function f of x, and this is my limit, 16. So we're able to show that if this is true, if x is within distance root epsilon from 5, then f of x is within distance epsilon from 16. All right, and that is the end of 1.7. Go ahead, take a break, stretch your legs, then you got to make sure you're trying some of your web work, homework problems. All right, I'll see you guys next time in 1.8.